Everyday life is a series of rapid transformations. Water rolls into a vigorous boil on one side of the stove, while an egg firms up in a hot pan on the other. At a glance, both look like simple, one-way processes. But which of these changes can actually be undone? Our intuition is often an unreliable narrator. Some changes that look permanent, like an ice cube turning into a puddle, are easily reversed. Others, like the charring on a piece of toast, alter the structure of the matter forever. Moving past simple assumptions requires a more rigid system. We need a blueprint to decode the mechanics of these alterations, a way to see the specific how and why behind every material shift. Deciphering these shifts requires more than a glance. It requires a framework that tracks the invisible chemical and physical rules governing the objects we interact with every day. Consider the loop. In water's familiar cycle, ice melts into liquid, evaporates into gas, and condenses right back into droplets. This is a physical, reversible change. Throughout the entire process, the molecular identity of the substance remains identical. Because the molecules haven't changed, the water can always return to its original form. Then there are one-way streets. These are irreversible changes, where a process breaks down the original matter and reshapes it into entirely new substances. This photograph shows a magnesium ribbon burning. The intense reaction doesn't just change the shape of the metal, it creates a white powder called magnesium oxide. This is a new substance with properties completely different from the original solid ribbon. However, look at the graphic in Activity 1. Breaking a wooden stick is a physical change because the wood itself hasn't turned into a new substance. But because the structural damage is permanent, you can't simply reverse the process. Identifying whether a change is a loop or a one-way street is the first step in knowing if an alteration to our world is a temporary state or a permanent reality. Some changes are deceptive. When you dissolve sugar into water, the solid disappears. Visually, it looks like an irreversible one-way street. But look at the setup detailed here. By heating the sugar solution to concentrate it and then allowing it to cool, we find the solid sugar crystals left behind in the dish. Dissolving is actually a physical loop. Both substances can be recovered unchanged. To understand why these loops and one-way streets happen, we have to look at the invisible engine driving them: energy transfer. In an endothermic process, heat is absorbed to trigger change. Energy pushes into an egg to break its molecular bonds. Exothermic processes do the opposite. A burning candle releases stored energy outward, pushing heat into the environment. Tracking whether a change absorbs or releases energy reveals the true mechanical cost required to make that change happen. This diagnostic flowchart brings these concepts together into a single blueprint. It allows us to classify any change by looking at identity, reversibility, and energy. The first step is to check for a change in identity. If new substances with different properties are formed, the blueprint classifies it as a chemical change. Next, we look at the path. Can the process be undone? This separates the reversible loops from the irreversible arrows. Finally, we map the energy flow. We determine if the change was powered by heat moving inward or if it aggressively released energy back into the world. Apply this to a common scenario: iron rusting in the rain. As the textbook notes, iron reacts with oxygen and water to form rust, an entirely different substance. Because you cannot turn that rust back into iron through simple physical means, it is a permanent chemical change. This system provides a repeatable way to analyze the world around us. By mastering these specific rules of reversibility and energy flow, we can look at any material and predict exactly how it will respond to a change.